Welcome, ladies and gentlemen, to Complex Variables. Where'd that come from? Um, we're going to study some more of the beautiful theorems of complex variables that don't happen anywhere except this. And so I'm looking forward to it. You remember that last time we proved Liouville's theorem, which is one of the most succinct and lovely little theorems in complex, namely that a bounded entire function is the emergency room function. It's constant. We're going to see an amazing theorem in a few minutes that shows that if something is true for the real numbers, that same thing is true for the complex numbers, and that's an extremely powerful theorem. So I'm looking forward to getting to it. But the first thing that we're going to prove as soon as we pray is that we're going to prove a lemma that helps us to prove the fundamental theorem of algebra. Does that sound like the most fundamental thing? I mean, it's the center of the universe in algebra. Namely, that if you have a polynomial over the complex numbers, all of its roots, did I say all of its roots? All of its roots are inside the complex numbers. We know that's false for the rational numbers. We know that's false for the real numbers. But for the complex numbers, if you have a polynomial whose coefficients come from the complex numbers, all of the zeros of that polynomial are in the complex numbers. And it's a full set. It's a full set of them. If you have a polynomial of degree n, there are n of those roots. So we're going to have some fun today. Let's pray and go. Father, in the name of Jesus, thank you so much. Thank you for the beauty of this mathematical creation that you've given us. Thank you, Father, for each other that you've given us, Lord, that people who are anxious to learn can overcome horrific circumstances, even a disease, to check it out on the internet and watch and be faithful and do homework problems. Thank you, Father, for these people, and thank you for the opportunity to lead them today. In Jesus' name, amen. All right. Can't wait to get started, so I'm not going to. Lemma. As you know, a lemma is something to help us prove some bigger thing, and the bigger thing is the fundamental theorem of algebra. So let's start. If P is a polynomial, and the degree of P is greater than or equal to 1, then the limit as the absolute value of z goes to infinity of P of z is infinity. I should put this in absolute value as well, so there's no confusion. But this is something you've known for a long time. Even for a real polynomial, if x goes to infinity, then p of x goes to infinity, as long as there's actually an x in the polynomial. Well, the same thing is true in the complex plane. So let's prove it. And we're going to prove it by induction on the degree of p. Okay, well, it says n is greater than or equal to 1, so we start with the first domino, n equals 1. Then P of z looks like az plus b. Those are the only polynomials of degree 1 that I know where a is not 0. Okay, so let's compute the absolute value of P of z. Big surprise, that's the absolute value of AZ plus B. But this is greater than or equal to, this is one of the triangle inequalities, easy to prove from the one that you're familiar with, but you're probably familiar with this one as well, that this is greater than or equal to the absolute value of the first part minus the absolute value of the second part. Okay? It's less than or equal to the sum of the absolute values. It's greater than or equal to the difference of the absolute values. And so this is equal to the absolute value of A times the absolute value of Z minus the absolute value of B. And this goes to infinity as the absolute value of Z goes to infinity, right? If this goes to infinity, and this is now some positive number because A is not equal to 0, then this thing goes to infinity, this doesn't go anywhere, so the whole thing goes to infinity. So the first domino drops. Now suppose the theorem holds, or the lemma holds, for some m greater than or equal to 1. And of course we know it does hold for some m, it holds for 1. But suppose that it holds for any m greater than or equal to 1. We must show that the lemma holds for m plus 1. So let P of Z be a polynomial of degree m plus 1. Okay? Hopefully that's the natural place to go. One of the things that I like to teach, math students, no matter at what level of difficulty their course is, I always like to teach math students, when you're proving something, go to where the proof is forcing you to go. Now the degree of P is an integer, so it's likely that I'm going to prove the thing by induction. So I start doing it by induction. I do n equals 1. I didn't know how I was going to start off when I started proving it, but I knew what a polynomial of degree 1 looks like, and so this kind of fell into my lap. Now, what's the next step of induction? There's nothing else that I could do except, let's suppose the theorem holds for some m greater than or equal to 1. Greater than or equal to 1. Okay, suppose it holds for some m. Now I have to prove it for m plus 1. What do I have to prove? That if P is a polynomial of degree m plus 1, then the limit of P of Z is equal to infinity as the absolute value of Z goes to infinity. So I didn't have any choice. This is where I had to go. Now, then P of Z divided by Z minus A1 I'm not even going to do that. We'll do that little trick in the fundamental theorem. This one's easier. Well, that's going to be easy also, but let's do it this way. Then the absolute value of P of Z, my polynomial of degree m plus 1, is equal to the absolute value of a sub m plus 1, z to the m plus 1, plus blah, 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 plus a0, which is equal to Now I'm going to factor a z out of all the parts where I can factor the z. So this is going to equal the absolute value of z times the absolute value of a sub m plus 1 z to the m plus blah, 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 plus a sub 1, and there's no z left for a sub 1 because I factored it out, but then plus, I don't need this yet. Yes, I do. No, I don't. Let's see. This is greater than or equal to. I'm going to use the same trick that I used over here. The fact that the absolute value of the sum of these things is greater than or equal to the difference of the absolute values. I'm going to use the same trick here. That this is greater than or equal to, and I'm going to put the A0 in absolute value at the tail. Okay, that's certainly, if I split this off from the sum, then this whole thing is greater than or equal to this part up to A1 minus the absolute value of A0. So there's my trick. But this is to the m. It's not a very good m. This part here is a polynomial of degree m, and I'm assuming that the theorem holds for a polynomial of degree m. So since absolute value of z goes to infinity, and by induction, by the induction hypothesis, the absolute value of a sub m plus 1 z to the m plus blah, 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 plus a sub 1 goes to infinity. I'm forgetting about the a0 for right now. This goes to infinity. Then when I glue this stuff together, subtracting a constant is not going to affect the infinity. So I get that P of z in absolute value goes to infinity as z does, as the absolute value of z does, QED. So there's my lemma. Okay. Now, let's use this in order to get what's really pretty much the biggest theorem in algebra, namely the fundamental theorem of algebra. It's so important that I'm going to write out all the words. If P of z is a polynomial, of degree n, then P of z has n roots in the complex numbers if we count for multiplicity. Now, what do I mean if we count for multiplicity? I mean if z, if I have z squared minus 1 squared, that's a 4th degree polynomial. And its roots are 1, minus 1, 1, and minus 1. It's a fourth degree polynomial. It has 4 roots. They're counted twice, but and that's what I mean by counting with multiplicity. I count each one at a time. Okay. Okay, how do you suppose we're going to prove this? You always want to ask yourself that question. Am I going to do it directly by brute force? Am I going to do it by contradiction? Or am I going to do it by induction? And I think it's pretty obvious that since all these n's are flying around in here, we're going to do it by induction. So, proof. By induction. First of all, let's take care of the trivial case. Suppose P of z has no roots. Okay? i.e., P of z is not 0 for every z in the complex plane. Okay? Seems like kind of a trivial case, but let's handle it. Then let f of z, and this is a trick that I want to get you accustomed to this. This is a trick we're going to use often this semester. Let f of z be 1 over p of z. If this is never 0, then I can divide by it. So f of z equal 1 over p of z is analytic everywhere, so it's entire. Okay, that's an entire function. Also, the limit as z goes to infinity of f of z, absolute value of f of z, is equal to 0. Okay? Now, why is that? Well, I should have said n greater than or equal to 1. We're not talking about 0-degree polynomials here. We're talking about because a 0-degree polynomial has no roots whatsoever if the constant term is not 0, and it's nothing but roots if the constant term is 0. So that's a trivial case we don't care about. So this is the case for n equals 1. If p of z has no roots, but it's a polynomial of degree 1, then I'm dividing by az plus b here, and so the limit of that thing is equal to 0 as the absolute value of z goes to infinity. Okay, now choose some positive number r large enough so that this absolute value of z is less than or equal to 1 for all absolute value of z less than, greater than or equal to r. In other words, if as the absolute value of z becomes infinite, so it's out there someplace, if the function's going to 0, then that means that for some r big enough, all the function values in absolute value have to be less than or equal to 1. This isn't really clear. Okay, eventually it's got to be less than or equal to 1, otherwise the thing couldn't go to 0 out there. So for some r large enough, everything beyond r, the function in absolute value is less than or equal to 1. Okay, now what do I know about f of z? or P of z. Did I write f of z? Yeah, f of z is the reciprocal, sorry. I'm going to wake up any moment now. F of z less than or equal to r. Since f of z, since f is continuous, now why is f continuous? Because P of z has no roots. So when I divide, I'm not getting any zeros. So this thing is continuous. In fact, it's analytic. It's a very nice function. Since f is continuous, especially when absolute value of z is less than or equal to r, but it's continuous everywhere, it is bounded there. Why? Because a continuous function on a closed bounded interval has its maximum. It's certainly bounded by something. Hence, there exists some capital M such that the absolute value of f of z is less than or equal to m for all z whose absolute value is less than or equal to r. Okay? So we're making some progress here. There's some capital M that bounds absolute value of f of z for all absolute value of z less than or equal to r. Okay? Therefore, well, let's see. Absolute value of f of z is less than or equal to m for this. Absolute value of f of z is less than or equal to 1 for this. So all the time, the absolute value of f of z is less than or equal to whichever one of those is bigger. So the absolute value of f of z is less than or equal to the max of either m or 1, and that is for all z in the complex plane. Well, now look at that. I have a function that is entire, it's bounded, and so by Liouville's theorem, it's constant. Therefore, f of z is a constant. Now, what's wrong with f of z being a constant? Because f of z is 1 divided by a polynomial of degree, in this case 1, and that can't happen. So let's just write down that little detail. Turns out that dropping the first domino is really the harder of the two cases. Once I have the first domino going down, then the next one is easy. So therefore, P of z is a constant. Which contradicts P of z having degree 1. Degree equal to 1. Okay, P of z is not a constant. So we now have the first domino just dropped, case of n equals 1. Now suppose that the theorem holds for all polynomials of degree m. Greater than or equal to 1. For some m. Of course, we know it's true for that m, but suppose it holds for some m. Now, where is the theorem forcing us to go? We now have to go to planet m plus 1. Suppose that p of z is a polynomial of degree m plus 1. Suppose p of z has degree m plus 1. Okay? Now, I know, let's see. Consider p of z over z minus a1 where a1 is a root of p of z. You see, if p of z had no roots whatsoever, this exact same argument would show that that's not possible. So okay, it has to have at least one root, because if p of z had no roots whatsoever, I could form f of z equals 1 over p of z. And I know that this is a polynomial of degree greater than or equal to 1, so there are some z's in it. And so the limit of 1 over stuff with z's in it is going to be 0. So I could pick an r big enough so that this is bounded and that is bounded. And so the absolute value of the reciprocal is bounded entire function, therefore it's a constant, which contradicts the fact that the degree of p of z is not 0. Okay, so it's the same argument that I had before. So there is a root. Now, therefore, p of z over z minus a1 is a polynomial of degree m. If I take a polynomial of degree m plus 1, then just by longhand division, I would get it coming out even, and what the result would be is a polynomial of degree 1 less after dividing by a polynomial of degree 1. Okay. So by the induction hypothesis, p of z over z minus a1 has m roots. thus tossing A1 back in, P of Z has exactly m plus 1 roots as needed. And now, time for me to take a drink of water. Okay, now let me do a little erasing. I alluded to this next theorem a little while ago. This is another incredibly powerful theorem. We're going to get a huge number of results from it. So let's start milking this cow. It's called the limit point theorem. And it goes like this. If f is analytic, and in fact, okay, let's do it the usual way. It's holomorphic in omega, where omega is a region. So the usual setup. And Z sub n is a sequence that lies entirely within omega. That's not a very good for every n in n, such that Z sub n converges to Z sub 0, and Z sub 0 is in omega. So Z sub 0 is a limit point of this sequence. And if f is a function that is 0 at all the Z sub n's, then f is identically the 0 function. And this is still on omega. Now, let's take a minute and think about what this thing says. If I have a function that is 0 on every element of a sequence, and that sequence converges to some point that is also in my region there, then the function is identically 0. It's the 0 function everywhere in omega. Now, what does that mean? Let's take the extreme case. Suppose that I know that a function is equal to 0 for all real numbers. And I want to know if it's equal to 0 in some big omega. Well, if it's equal to 0 for all real numbers, then I could take any sequence as long as not all of the Z sub n's were equal to Z0, if there was an honest to goodness sequence. And if the function's equal to 0 at all these places, and those places converge to z0, then the function is 0 not only at this point, but everywhere in that region. Can you imagine the power of this thing? I look at things on the real line, and it tells me what they're like all around. This is a gargantuan theorem. So let's, maybe it's not true. Let's see if we can prove it. That'd be a joke if it wasn't true. But if it's not true, going where the proof forces us to go is going to open that up to us. So let's see how we would prove this. Proof. Well, let A be the set of all points in omega, z and omega, such that z is a limit of zeros of f. Okay? So I'm going to let A be all the points in omega where z is the limit of zeros of f. That might just be real numbers right now. But all the points where this function is 0, that's going to be the set A. Okay? And let z0, z sub 0, be one of those guys. Since f is analytic, f has a power series it's analytic on omega, and z0 is in omega. So f has a power series centered at z0. And we know what that power series looks like. It's the Taylor series. F of z is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at z0 divided by n factorial and multiplied by z minus z0 to the nth power. That's the Taylor series for f centered at z0. Now, let's prove that all those derivatives, let's prove that the nth derivative of z0 is equal to 0 for all n greater than or equal to 0. Now that'd be a powerful thing. Okay. For contradiction, suppose this is false. Suppose that all those derivatives, or the function itself, are not 0 at that point. So suppose this is false. And choose, and let m as in Mary, be the smallest integer for which it's false. The smallest integer such that the mth derivative of the function at z0 is not 0. I want to prove that they're all 0. If I want to do it by contradiction, then okay, suppose that m is the smallest integer for which it's false. And I want to see if I can get myself into trouble. So therefore, in some open neighborhood, of z sub 0. F of z is equal to, now, here's my Taylor series, but I know that maybe a bunch of them are equal to 0, a bunch of these derivatives, but eventually, if I'm doing this by contradiction, eventually there's one of them, the mth one, that's the first one for which this is not 0. So then f of z is equal to z minus z0 to the mth times its own infinite series, the mth derivative at z0 divided by n factorial, m factorial, plus z minus z0, the m plus first derivative evaluated at z0 divided by m plus 1 factorial, plus et cetera, that goes on as an infinite series. So this is equal to z minus z0 to the mth times, and the rest of this mess I'm going to call h, times h of z, okay? And of course, since we know that f is continuous, it's even better than continuous. Since f is continuous, h is continuous. Okay, so that's what we have so far. Let's do some erasing. Gabe, I should let you erase the board this time. Okay, making progress. Thus, it was about time for a thus. If h of z0 is not 0, there exists a small disk around z0 such that h of z is not 0 for all z in that disk. Okay. Call the disk D. Okay. By continuity, if it's not 0 someplace, if it's not 0, I'm sorry, it's Z0, then there's a little disk around Z0 where it's not 0 because it can't instantly start being 0 because of continuity. So, therefore, f of z is not 0 on D slash Z0. Because the only place that f of z is 0 is at Z0 or wherever h would be 0. But if h ain't 0 in this disk, then neither is f. But Z0 is in A. a limit point or an accumulation point of the zeros of f But what's wrong with that? Well, I'm going to stick one other thing in here, and I apologize for this. I said it earlier when I was describing it with my hands, but I didn't say it when I was describing it with my pen. If not all z sub n equal z sub 0. If all of the z sub n's are z sub 0, then there's nothing really happening here. There's no accumulation point. I need a sequence that's actually moving towards z sub 0. I mentioned that before. So here I've got an accumulation point, z0, and I've got a bunch of things that are marching towards z0, but in some disk that's punctured with only one point missing, that f of z is not 0, f of z0 is not 0, and f of z is not 0 in this entire disk. Well, wait a minute, because I've got all of these points that are approaching z0, and the function is 0 at those points. That's not possible. So this is a contradiction. And that contradiction polishes off the theorem, limit point theorem. Now, I did need that f was analytic at z0. Let me show you why. So I'm going to make that comment. We did need, this theorem is not necessarily true if f is not analytic at z0. We did need that f is analytic at the point z sub 0. Here's an example. Suppose that I let f of z be the function 1 over, no, let's not do that. Let's do it the other way. Let's make it the sine of 1 over z. Okay? This is not analytic at z equals 0. Okay? This function gets into real deep yogurt at z equals 0. But let's take a look at the following sequence. Let z sub n equal 1 divided by n pi. Okay? Clearly, f of z sub n equals 0 for all n, because the sine of 1 over z is the sine of 1 over this, and 1 over n pi is n pi. The sine of n pi is equal to 0, so f is 0 on all of these points. And the z sub n's go to 0. This converges to 0 as n goes to infinity. So the limit as n approaches infinity of z sub n is equal to 0. But the sine of 1 over z is not equal to 0. It's not equal to anything. So we needed a full hypothesis. Okay. Let's do some more erasing. Now, just to start showing the power of this thing, let's do a little corollary, which is trivial to prove. Namely, if F and G, wow, didn't get the board dry enough. See, Gabe, you would have done a much better job than I have. If F and G are both analytic, on omega, a region, and Z sub n are in omega, not, I'm going to write it down this time so I don't have to fix it later, not all Z sub n equals Z0. Z sub n converge to Z0 in omega, and if f of Z sub n equals g of Z sub n for all n, so that's a pretty powerful thing. If they agree on all of this sequence, then not only are they equal at Z0, they're equal everywhere in omega. That's a hugely powerful thing that we just proved. Then f of Z equals g of Z for all Z in the region. Huge, huge theorem. Proof. One line. Apply, and many of you already see this coming. Apply the limit point theorem to the function f minus g. End of proof. So it's not only about a function being 0, it's about two functions agreeing on some sequence. Then they agree everywhere in the region. This is just a monster theorem. Okay. I want to work some examples that I worked up here. So let's do this. Examples. Prove. I'll learn how to spell prove any day now. Prove that sine squared z plus cosine squared z equals 1. Now, how are we going to prove this? Where does the proof force us to go? If I'm going to use this corollary, then I need two functions that are analytic on omega. And by the way, I want to prove that this is true for all z in the whole complex plane. Omega is everything, okay? Then I need two functions that are holomorphic on omega. Sine squared z plus cosine squared z is holomorphic everywhere. It's an entire function because it's easy to take the derivative. The function 1 is holomorphic everywhere because it's easy to take its derivative. Wonder what that could be. So I've got two functions that agree where? Well, we know that they agree on the real number line. That's just trigonometry. So let's do the solution here. Let z0 be an accumulation point. For a set of real numbers between, say, minus m and positive m, where m is arbitrary. I don't care what m is, capital M. Okay? Then because z0 is an accumulation point for some set of real numbers, then since sine squared of z plus cosine squared of z and 1 agree on the real numbers, and let me give myself some space by doing some more erasing. Then, I already have then. I don't need another then. For all z such that the absolute value of z is less than m, sine squared z plus cosine squared z and 1 agree at z. So the idea is this. Here I've got some big set. I've got z0 here on the real number line, and I've got some sequence that's approaching z0. And all of these places are on the real number line, which means that these two functions for the reals coincide. And so at z0, since I've got that accumulation point here within omega, then f of z and g of z agree everywhere in omega. That's a hugely powerful theorem. So now that's true for every z whose absolute value is less than m. But m was arbitrary. So I could take bigger and bigger m's. So they agree on all of the complex numbers. Just because I have accumulation points in the real numbers and they agree at sequences in the real numbers, that gives it to me for the whole complex plane. Or if the function was limited to be analytic on some region, well, it gives it to me on all the points in that region. Okay, let's do another example. This one, the solution is by sneaky trick. But hopefully you're getting the idea. If I have holomorphic functions that agree on the real numbers, they agree through the whole complex plane. So let's do another example. Find a closed form expression for f of z equal to 1 over z times the sum from n equals 2 to infinity of minus 1 to the n plus 1 z to the 2n minus 1 over 2n minus 1 factorial. Okay. This is actually 2n minus 2, and this is 2n minus 2. My fault, and this is not 1 over z yet. So, as my wife is always telling me, don't listen to what I say, just know what I mean. Okay, f of z is equal to this power series. Okay. Power series, you might have guessed, is not entirely at random, because here's the solution by sneaky trick. And it's exactly what I was about to write. F of z, what I did write, is 1 over z times the sum from n equals 2 minus 1 to the n plus 1 z to the 2n minus 1, because I've pulled out one of the z's, divided by two n. Oh my gosh. This one was not supposed to change. Only this one. My fault. Let's go back to the very beginning. Suppose I pick a function at random. F of z is equal to the sum from n equals 2 to infinity of minus 1 to the n plus 1, z to the 2n minus 2, divided by 2n minus 1 quantity factorial. That's my function. And here's the sneaky trick. I want these powers, the power and the number inside the factorial, to agree. So I pull out the 1 over z, and now that increases this power by 1. Okay, now that is equal to, now this is a typical excuse me, this is a typical trick in power series. Let's change the limits of integration. The infinity certainly isn't going to change, but this is 1 over z times the sum from, let's use a different variable, say k equals 1 to infinity, of minus 1 to the k, z to the 2k plus 1 divided by 2k plus 1 factorial. Okay, so I'm going to pull up a chair. You don't have to see me. You have to see the board. Does this second power, this last power series, does that look familiar? Well, except for the 0th term, this thing is sine z. Notice the odd powers, the odd factorial. This is the Taylor series for the sine of z with one term missing. So this is equal to 1 over z times the sine of z and then minus z over z, so minus 1. But when is that true? We know this is the power series for sine of x. The sine of x is the sum, actually from k equals 0 to infinity of minus 1 to the k, z to the 2k plus 1 over 2k plus 1 quantity factorial, x to the 2k plus 1 over 2k plus 1 factorial. That's the Taylor series that's the Maclaurin series, in fact, for the sine of x. So on the real number line, which is just full of accumulation points, this is the real power series. So this is equal for all z in R, hence, by the limit point theorem, for all z in C. So finally got that all patched up. Nice stuff here. Let's do one more example. All right. Now, a similar example. Find a closed form expression. Now you probably noticed from that last one what I meant by a closed form expression is f of z equals some function of z where I don't need a power series to do it. Okay? That means the same thing here. Find a closed form expression for f of z equal to the series n equals 1 to infinity z to the n divided by n with no factorial, just z to the n over n. Okay? And here's the solution. What's the derivative of f of z? Well, we differentiate it term by term, so the derivative is n z to the n minus 1, but the n's cancel, and I just get z to the n minus 1. So the derivative is the sum from n equals 1 to infinity of z to the n minus 1, which I could rewrite just changing, going down by 1. I can use a k here. So if, for k equals 0 to infinity of z to the k. Now, what is this series? We've seen that a million times. That's 1 over 1 minus z. Now, I don't want f prime, I want f. So what do I do to f prime in order to get f? And the answer is I integrate it. So the integral of 1 over 1 minus z dz, just the antiderivative, we don't have any curve or anything in here, I do by substitution. Now I warned you not to depend too much on substitution, but if we stay away from the problems, we can do it. So let's just do it for real numbers. Let's change this to an x so you know that I'm not doing this in the complex plane. Okay, so if u is equal to 1 minus x, then du is minus dx. So this is equal to the integral of 1 over u times minus dx times minus du. So I can pull out the minus sign. And the integral of 1 over u is minus, the minus 1 over u is minus the natural log of absolute u plus some constant. Okay. Now, if the absolute value of z is less than 1, then f of z is equal to minus the natural log of u, which is 1 minus x. In this case, it'll be 1 minus z now, because I never quite get to 1. The absolute value of z is less than 1. And still plus a constant. But what's the constant? Well, f of 0 is equal to 0. Because 0 is a real number, and we know this power series. So f of 0 equals 0. So that implies that minus the log of 1 minus 0 plus c equals 0, and that implies that c equals 0. So we're done. F of z is equal to the negative of the log of 1 minus z. So another time when the limit point theorem comes through for us. So we're going to end there. That's a natural place to end. Next time we're going to start looking at residues, which is one of the biggest parts of complex variables. So stay tuned and make sure that you continue to stay up on the homework problems. Otherwise, you get killed. I want to make this announcement, so hold on for a few seconds. I've had a number of people who have told me that they were counting on having 3 in-class exams in order to help control their grade for the semester, just in case they did lousy on the assignments. And they said, oh, please have grace since the rules have all changed. And so I'm going to have grace since the rules have all changed. I do want to point out that without doing well on the assignments, there would have been no hope of doing well on the exams. So hopefully everybody is really pressing hard to understand the assignments. You're really calling me all the time to get answers to your questions. You're texting me like crazy in the middle of the night to get answers to your questions. But if that's not you, you've got to change. Okay? That's not the grace part. Here comes the grace part. If you were counting on the assignments to give you a better grade, and now you find out that the assignments, except for one exam that we already had, all of these assignments are going to count for everything except for a take-home final exam, then if you have some assignments that you've already done that you're not happy with the grade on it, the grace is, I'm going to let you do them again. You can go back, you can redo an assignment from the beginning of the course until now. It's not going to be true. You're not going to get to do assignment 7 and assignment 8, do them twice. But the assignments that are already assigned, if you need to do them again, get them right. And of course, if you're doing what I've begged you to do all semester, you're practically living with me on the phone. Okay? But if you're not that kind of person, you have the choice. It's perfectly all right if you decide not to succeed. I know a lot of you are calling me a lot, texting me a lot. Those people are going to succeed because they're nailing the assignments. So please take this grace with, for all that it's worth. It's worth a lot. And the rest of the semester, finish well. Don't ever miss one of these classes. You'll notice that they're on YouTube. So if you miss it during class time, you get to go back and watch it. Okay, everybody's probably noticed that already. You can watch each class 19 times if you want to, until you're sure you understand it. Be diligent. Success comes to the people who do the right thing diligently. Diligently. A's aren't free, but there's no excuse for anybody not getting an A in this class with what you just heard. So, God bless you all. We'll talk to you soon.